Hello and welcome to the DataStax Developers YouTube channel. I'm very pleased to announce we have a special guest today, and Daniel from RocktheJVM, an up-and-coming YouTuber who focuses on Scala, Akka, and distributed systems. He's here to give you a masterclass today in CQRS, or Command Query Responsibility Segregation, with event sourcing, Scala, Akka, and of course Apache Cassandra. Daniel, thanks for being with us today, and take it away.
Hi everyone, and welcome to CQRS with event sourcing and Scala, Akka, and Cassandra. This video is a live coding tutorial of how to implement the CQRS pattern in your own application and how to run it on DataStax's Astra DB service. My name is Daniel, and I'm a software engineer and instructor. I've been teaching everything in the Scala ecosystem in live and online training for more than 8 years now, and I've had the privilege to train high-performing teams at companies like Apple, Adobe, and Microsoft. I also run this website called RocktheJVM, which has long-form training material on the Scala language, effect systems like CATS and Zio, data streaming with Apache Flink, big data with Apache Spark, and distributed systems with Akka, which is what we are going to use in this video. I have more than 230 hours of material on the site, so there's a lot to feast upon if you're ever interested in the Scala world. Now, the objective of this video is to demonstrate an implementation of CQRS and event sourcing with Scala, Akka, and Cassandra. Now, these are very powerful tools used in many high-throughput applications and high-profile companies around the world, and this video is a demo with a realistic scenario dealing with high-load Scala-grade problems. Now, this demo is for you if you're curious to see these technologies and tools in action, or if you want to learn what CQRS is and how it's different from other models of storage. Now, I recommend that you use this video in one of two ways, either as entertainment and a way to satisfy your curiosity, in which case I'd recommend you simply watch what I'm doing and see the effects live, or you can follow along and get your hands dirty as I write code on camera. I like to demonstrate by doing, so I write live code in all my courses at RocktheJVM and in demos like this. Now, the structure of the demo is as follows. First, I'm going to introduce CQRS and event sourcing as design patterns, as well as the Akka persistence tool that we're going to use in the video. After that, I'll walk you through the starting project setup, and then for most of the video, we're going to do live code and testing locally on a Docker-based Cassandra instance. And finally, at the end of the video, we're going to take the official DataStax Astra DB service for a spin with the code that we implement in the video. Now, everything is coded live on camera, so you can find links to the GitHub repository and all the resources that we use in the code, and you can find them in the description of the video. The demo will be quite big, so I'm going to speed up some coding parts, but I've edited the video so that you can pause it and follow along still. I'm going to leave nothing unexplained as we follow through this video. Now, with that said, let me introduce the core concepts of the video. First, CQRS comes from Command and Query Responsibility Segregation, which is a design pattern on how to organize your code and data while interacting with a persistent store. Complex applications with high data access concurrency might find themselves in a rut. Sometimes there are different models or performance requirements for reads and writes. For example, if the number of stakeholders is disproportionate on one side, or there might be the risk of data access contention because of such concurrency, or the unifying of the data model will likely make it too complex to manage. And there's also data security compliance, which is hard to enforce on shared data. To that, we have the solution to separate the read model from the write model and organize your code in terms of commands which can be applied. And these commands will be additive and will have the role of changing your internal state, while queries will be separate and will investigate the current state of the system. So the picture in a broad sense will look something like this, with one side writing to the database using a write-specific data model, while another stakeholder reads data appropriate for them using another model. And these two models for read and write will be synchronized with some tools that we're going to see in the code. Now, the use cases for CQRS include applications with high data access concurrency and task-based applications. For example, a hotel booking, which is what we're going to see in the code, or an online store, and I'm going to show you some examples. Also, CQRS is appropriate for applications with different read and write performance requirements. For example, if you have a disproportionate number of readers, you have different performance requirements for the read side compared to the write side. Also, as we will see in the code, CQRS is especially appropriate for the situations with with a high likelihood of schema evolution. That is the situation where you have to change the structure of your data, which is particularly painful in regular CRUD applications. Obviously, CQRS is not to be used with simple CRUD logic, so simple databases where you simply store the latest state in the database directly, or for infrequent data access, because CQRS is also built for a specific kind of performance. Now, CQRS is often paired with another design pattern called event sourcing. Now, event sourcing is appropriate for the situations when the current state of the system will change all the time, but you're also interested in querying a previous state or in tracing how you arrived at the current state. Examples include tracing orders in an online store, or tracing the transaction history in a bank, or the chat message history or document versioning in a shared repository, or as we will see in the code, we have a hotel booking system. Now, let me give you a relatable situation. Let's say we are interested in designing an online store and we want to trace an order. So we're asking for all the data about an order. In a regular CRUD-based database, if we want to investigate the state of a particular order, we get a single row, which is a traditional relational model, select star from whatever orders, and give me the latest status. Whereas we can have a much richer description of the status of the order by tracing all the events about the order. So a table might look something like this, where an order might be created, the inventory will be allocated, the order will be dispatched, delivered, or it may be returned, canceled, refunded, and there are a bunch of stuff that can happen with that order, and you can track everything that happens to it. So instead of storing the current state, which is refunded, and we haven't learned too much, we can also ask why the order was refunded, so we can store all the events that led to the current state. And we can always recreate the current state by replaying all the events in order. Now, to implement the event sourcing pattern, we're going to use a tool called Akka Persistence. If you've never heard about Akka before, it's a powerful toolkit that will implement the actor model. The actor model will organize your code into so-called actors, which are independent encapsulated entities with their own state and behavior. They're fully encapsulated, so they're not available for regular object-oriented method calls, but you can only communicate with them via asynchronous message passing. Now, because they're fully independent and asynchronous, you can spin up a large, very large amount of these independent actors and schedule them on a relatively small throughput for an incredibly high throughput of your application. Now, these are normal actors. We will use a special breed of actors called persistent actors, which come with extra capabilities. Every persistent actor will have a unique persistence ID, and this actor can persist events to a long-term store. So this can store events into a database such as Cassandra. A persistent actor will also be able to recover its own state by replaying events from the store. So when an actor receives a message, which we will call command from now on, it will asynchronously persist an event to the store, and after the event is persisted, it will be able to change its internal state. Now, when the actor is spun up or restarts because of an application crash or because of an application restart or upgrade, the actor will be able to replay all the events associated to its persistent ID and recover its state as if nothing had happened. So let me show you a quick picture. Let's assume that this is an actor. This blue blob is an actor with a message handler, which is the behavior, and the mailbox, which is used to store all the messages that you send to it. When one of the threads in the thread pool schedules to run this actor, the thread will simply dequeue messages from the mailbox, and it will treat every message atomically. Now, let's assume that this actor interacts with a persistent store. When the actor is scheduled to run on a thread, it will simply dequeue messages, and it will treat that message with the internal behavior of the actor, which is its internal code. Now, that behavior can do a lot of stuff, and one of the very often used effects is to persist an event to the persistent store. Once the persistent store acknowledges the persistence of that effect, it will notify the actor. This will be transparent to us as programmers, and when the actor receives this acknowledgement, it will change its internal state, and as an effect of that, it might send messages to other actors in the system. As I mentioned, we have lots and lots of actors in a Akka persistence system. And after the actor is done with the message, it will simply discard it and dequeue further messages for as long as it holds that particular thread. So a new message might be dequeued, treated by the handler, a new event might be persisted, some further messages might be handled, and so on and so forth, for as long as the actor has hold of that thread. Obviously, the thread pool will juggle between many of these actors, so from our standpoint, an actor is effectively a single-threaded business. Now let me show you a picture of what happens to an actor when an application starts or restarts for whatever reason. So assume that this is a persistent store and an actor is simply spun up when the application starts. An application with an actor with a persistence ID will simply ask the persistent store for all the events associated for that persistence ID. The persistent store will fetch all these events, and the actor will simply replay all these events in order, and the actor will recreate its internal state. So in this demonstration, we're going to implement a realistic scenario dealing with events at scale. We're going to imagine a hotel reservation system which manages bookings for 1,000+ hotels, although you can scale for much more than that. So we can treat millions of possible events in a short span of time, and we can deal with a variety of event types. The fundamental interaction is going to be between a hotel, which we are going to imagine as an actor, and the persistent store, which is going to be Cassandra. Each hotel actor will be a persistent actor, and we're going to implement event sourcing on that. Obviously, we're going to manage many hotels, up to 1,000 or even more than that, and we are going to manage all these hotel actors by some sort of centralized agent, which will in turn receive requests by some sort of front-facing API or application which manages bookings. This front-facing API is not really that interesting for our CQRS demo, so we will leave that aside, but I'm going to leave that to you as an exercise if you want to expose that. This is the write side. On the read side, we will have various hotel staff apps specialized for each hotel, which will monitor all the events associated with that particular hotel, and they will recreate the entire state of that hotel in terms of reservations so that they can query that state very easily for availability. So we will implement the CQRS pattern in which the write side, which is the booking service, will issue commands such as make a reservation, amend a reservation, cancel it, and so on and so forth, while the read side, which is the hotel management app, will inspect the current state for that particular hotel. And we can have many hotel staff apps independently monitoring their state. We will pair CQRS with event sourcing and Akka persistence, in which incremental events will be stored to Cassandra and the state of the system will be recreated by replaying all these events. So without further ado, let me show you the project. So I'm here in IntelliJ IDEA. I'm using the IntelliJ IDEA plugin for Scala development, and we will have a plain IntelliJ project with a bunch of resources and configurations and a playground application. You can check out the Git repository, which has a start tag, which you can check out to bring the state of the code in this state that you are seeing right now. Now let me quickly walk you through this project. We are going to spend all of our time under source main Scala. Here we have a playground application with a simple actor system that will simply test whether you have the library dependencies already downloaded and installed. Which brings me to build.sbt, which contains all the library definitions that we're going to need for this demonstration. Once you load this in IntelliJ, IntelliJ will take care to download all the appropriate libraries. Besides the playground application, we have a bunch of configurations which we won't really touch until the end of the demonstration. Application.conf in particular is of most interest to us when we want to change the connection from a local Cassandra to the cloud-based DataStax Astra DB. And besides that, we have a Docker Compose YML, which will spin up a local version of Cassandra for us to interact with. At the same time, in order to set up the appropriate tables, we have this little file called tablesetup.cql. This models the exact same scenario as the definitive guide book, which you can find on the DataStax website free of charge. If you're interested in checking that out, I pulled all the table definitions here in this file so that we can access them more easily and set up the appropriate tables once the Docker container starts. Now, speaking of the Docker container, I recommend that you open a terminal window on your computer and navigate to the directory where you downloaded the Git repository and run this command docker-compose up. I assume that you already have Docker on your computer. When you hit Docker compose up, if you haven't downloaded Cassandra before, this will take a little while. I've done this before, and the command spins up the Docker container much more easily. But leave the Docker container to start, and we will get back to the code. Let's test this application so that we can see whether our libraries were downloaded correctly. So I'm going to run this application, and if we see the string welcome to Akka in the logs, then we have everything well set. All right, now I'm going to start by designing the primary interaction between the hotel actor and the Cassandra data store. So here under the com.RocktheJVM, I'm going to create a new package. So I'm going to have com.RocktheJVM.bookings, and I'm going to design something that says actor. So this is going to be the package actor. I'm going to create a new Scala class. I'm going to call this hotel, and this will be a class that I won't really want to add to the Git repository. Leave me alone. And this will be the primary actor, primary persistent actor that will interact with Cassandra. Now, this hotel will implement a message protocol. So this hotel will only treat a bunch of messages because we're using Akka typed. So here under the package, I'm going to create a new package. Let's call this model. And here under model, I'm going to create the commands and the data structures that we're going to use for the rest of the video. So here under model, I'm going to create another Scala file. I'm going to call this protocol. And I'm going to remove the protocol class because I'm going to define a bunch of data structures. I'm going to speed up the typing a little bit so that we don't waste any time with that. Now, for every reservation, we're going to store the guest ID, the start date and end date for the trip, the room number, and the actor which we will use to interact with. Then the change reservation will contain the confirmation number of that reservation which was accepted, the start date, end date, room number, and the same actor which we will use to send replies to. And the cancellation will simply contain the confirmation number and the actor that we will use to communicate. Now, in order to store a reservation, I need to create a reservation case class, which is a simple data structure. So I'm going to call this reservation, and I'm going to store it in a simple file. Case class reservation will contain a guest ID, which is a string, a hotel ID, which is also a unique identifier, the start date, which is going to be a date, then the end date, which is going to be a date as well, the room number, which is going to be an int, and the confirmation ID, confirmation number, is going to be a string. So this is going to be our fundamental data structure, which is going to be wrapped inside the events that we are going to store in the Cassandra. So here, back to the models for commands. So this is going to be for commands. We're also going to store events that we will persist to Cassandra. And this is going to be a case class. Let's call this reservation accepted, which wraps a reservation. One for cancellation, so I'm going to call this reservation canceled. And we will have another one for a case class. Let's call this reservation modified or reservation updated, with an old reservation and a new reservation. So a new reservation as a reservation. So these are events. The commands are the kind of messages that the actor, the hotel actor, will receive from the booking service, and these are the events that will actually be persisted into Cassandra. Now, let's go back to the hotel actor and let's design that. Now, we made this hotel a class, but technically this class is never instantiated because an actor of type hotel is actually spun up by Akka, and it's defined in terms of its behavior. So I'm going to turn this class into an object which will only contain some quote-unquote static fields and methods. Now, this object will contain a case class that will store the state of a particular actor. I'm going to define that with a data type state, and this will contain some reservations for a particular hotel. So reservations as a set of reservation. Now, I need to import reservation from the model, so I will store every state of every actor as a set of all the reservations applied to that actor. Now, I'm going to define an apply method, which will allow this hotel object to be invoked much like a function, and the apply method will take a hotel ID as a string, and this will return a behavior. So the behavior is the piece of logic that Akka uses to handle the commands. So I'm going to have a behavior from Akka actor typed with the type command, which we have from the model. So I'm going to import everything in the model. So now we have the command, which is the type that this actor will receive as messages. And I'm going to use a special construct called event-sourced behavior. Event-sourced behavior will take 3 type arguments. First of all, the command, the message that it will receive, the event type that it will persist to Cassandra, which we don't have right now, and the state that this actor will store internally. Now, let me go back to the model, and I'm going to store the reservation accepted, update, and canceled as events. So I'm going to define another sealed trait. I'm going to call this event. A trait, if you don't know Scala, it's much like a Java interface. So this is the exact same concept. And now the event is known to us. The event-sourced behavior also has an apply method, which means that this can be invoked like a function, and the function will take a bunch of arguments. Persistence ID, and the persistence ID is a unique identifier from the point of view of the event store, which I'm going to use as persistence ID dot of unique ID with the hotel ID that I get as an argument. We got the empty state as an empty set, so I'm going to say state with an empty set. Then we have the command handler, and I'm going to define that as a method. So I'm going to have a command handler with the hotel ID as a string. And this is a function from the current state of the actor and the command, that is the message that the actor has just received, to an effect, which will have the event that is persisted into the event store and the new state of the actor. I need to import effect from the Akka persistence typed. And I'm going to leave it unimplemented for now. So I'm going to pass this command handler with the hotel ID as the third argument of the function. And we have an event handler, which I'm going to use very similarly. I'm going to have another method. I'm going to call this event handler. So event handler, which takes the hotel string. And this event handler will also be a function from the state of the actor at that point, the event that has just been persisted, and the new state of the actor after persisting that event. So I'm going to have my event handler with the hotel ID. So the fundamental interaction will go as follows. This actor will receive a command at some point, of course asynchronously. When that happens, the command handler will be triggered by modifying the internal state of the actor. We'll trigger an effect that will persist that event to the persistence store, in this case Cassandra. So once I receive this command, I will persist an event. I will create it and I will persist it. And after the persistence store has acknowledged the event, the second event handler callback will be invoked and the state of the actor will be modified after that. Awesome. Now let me go implement the command handler. This is a 2-argument function that contains the state of the actor at this point and the command that I'm just receiving, and I need to perform an effect. Now I need to perform an effect, a different effect, depending on the state of the command. So if the command is a make reservation, I need to perform some logic, change reservation, cancel reservation, different kinds of logic. Of course, you can add multiple commands if you want. So I'm going to run a pattern match. So I'm going to say command match. And in case we get a make reservation for all the constituent parts, I'm going to run the following logic. First, I'm going to find if there's any conflicting reservation for the hotel plus room interval that I have here in my reservation. So if this combination conflicts with any reservation in this set, then I'm going to return some sort of failure. Otherwise, I'm going to persist. I'm going to say reservation accepted. So I'm going to run a quick logic to check whether there is a conflicting reservation that I'm attempting to make. Now, to that end, I need to be able to compare reservations for overlapping intervals and also compare these for equality because I'm storing them in a set. So let me go back to my reservation data type and let me add a little piece of logic. The first piece of logic is an intersect function which returns true if two reservations have the same room in the same hotel and their intervals overlap. So we're comparing the hotel ID and the room number and the intervals for overlapping. The second piece of logic is equals in hash code because we're storing these reservations in a set. Now, for the purpose of this demonstration, we're going to consider two reservations equal from the point of view of the set if their reservation numbers, their confirmation numbers, are identical. So reservations are unique by their confirmation numbers. Now, in order to be able to create a reservation, we need to be able to somehow generate confirmation numbers as randomly generated strings, much like Airlines do. So I'm going to create a companion object reservation where we will store the quote-unquote static fields and methods of this type. And I'm going to have a single method called make, which will create a reservation based on just guest ID, hotel ID, start date, end date, and room number, and leave the confirmation number to that logic to be generated. Now, in order to implement that, I'm going to randomly generate a string of 10 characters, which will contain only capital alphanumeric characters. And I'm going to return a reservation after I've generated that string. So this is a simple utility method that will allow me to make reservations very, very easily. Now, let's get back to our code in hotel. So in the hotel actor, we will need to create a tentative reservation, and we will get to find some sort of potentially conflicting reservation in this set. So I'm going to create a tentative reservation. So tentative reservation as reservation.make with guest ID, and we're going to pass all the arguments here. And I'm going to try to find a conflicting reservation. So I'm going to have conflicting reservation. I'm going to use an option here, which is going to be state, which I receive as arguments. So the state here contains the whole set of reservations. So state.reservations find, and I'm going to find that reservation for which r.intersect this tentative reservation is true. Now the return value is going to be an option reservation, so option reservation, and I need to pattern match against this one. So if the conflicting reservation option dot is empty, then I have no problem and I can persist my event. So I'm going to have effect dot persist, and I'm going to persist this reservation accepted. So reservation accepted, wrapping this tentative reservation because I can make it. And after I've persisted, I can then reply or return some sort of confirmation to whichever actor sent me this command. So I'm going to have reply to the reply to actor, and the reply to actor is contained in the make reservation command. So I have the reference of the actor to which I can communicate, and then I'm going to store the current state, and I'm going to say reservation accepted for that tentative reservation. So this is the persist, and this is the reply to the so-called manager or booking agent actor. And otherwise, I'm going to return a simple effect that doesn't do anything, but rather replies with a command failure. So I'm going to have effect.reply, and I'm going to have a reply to, and I'm going to return some sort of command failure, which I haven't defined yet. I need to go back to the protocol and create that. So I'm going to create a case class. I'm going to call this command failure for a reason as a string, let's say, and this is the communication with the so-called agent, the main actor, and the hotel will reply back with a command failure, let's say command failure with reservation failed conflict with another reservation. Now, for some reason, the compiler is unhappy with my S thing, and this is probably because the reservation accepted doesn't extend event. So I'm going to make sure that all my types extend event. And if I do that, I can go back to my code and the function is interpreted correctly. All right, so all the events need to belong to the same trait because everything is typed, so the compiler type checks all. So this make reservation is only persisted if we have a non-conflicting scenario here. Now, in case we get a change reservation, for now, I'm going to return an effect.none because I'm going to try to test whether the make reservation effect was created. And I'm going to add another case for cancel reservation, and I'm going to, again, return an effect none. And I'm going to add a to-do here to change the logic in this case. Now, for make reservation, I would like to also handle the event that was persisted, which is reservation accepted, and we will modify the state of the actor to a new state. So I'm going to run a 2-argument function, which is state and event. Again, I'm going to run a pattern match on the event, so event match, and in case we get a reservation accepted for a reservation, I'm going to return a new state. So I'm going to have new state, save it as a val. So new state as state.copy, and I'm going to keep my reservations as state.reservations plus the reservation that has just been added. In Scala, collections are super easy to add or remove elements to and from, and I'm going to define, let's call it a print line, and I'm going to have my state changed, and I'm going to return a new state here in this s-interpolated string, and I'm going to return the new state as the end result of this function. Again, I'm going to add another case, and I'm going to add a to-do because we don't really need to return anything. I'm going to maintain the same state. Now, the to-do will act upon the reservation amended or changed and the reservation canceled events that were persisted. Right now, I want to test whether the make reservation effect was correctly created. So here under RocktheJVM bookings, I'm going to create an application. So I'm going to have a new package. I'm going to call this apps. And under apps, I'm going to create a, let's call this hotel test or hotel playground or something like that. So hotel playground. And I'm going to make it an object because this will have a main method that will turn this hotel playground into a standalone runnable application. So this hotel playground will have a main function. Now, I'm going to spin up an actor system that will hold one of these hotel actors, and I'm going to send a message to it. Let's see what this thing has. So first of all, I'm going to create a root behavior for the actor system. So I'm going to use a construct called behaviors, plural. So behaviors.setup. And setup takes a data structure called an actor context. so CTX. And I'm going to create a hotel actor and the so-called agent actor, which will simply log whatever replies the hotel will send back. So I'm going to have my logger actor as ctx.spawn. And actually, I'm going to make the compiler work with me here. I'm going to have my behaviors.empty, and I'm going to add a tag, a type argument to behaviors.setup. Let's say that this root actor system will receive messages of type string. Of course, we don't really need to send any messages to the root actor system, but I'm going to create a logger behavior. So I'm going to have, let's call this simple logger as behaviors.receive. And I'm going to use receive with any kind of message. So the simple logger will simply log whatever message it receives to the console. So I'm going to have my context and message as the 2-argument function. And I'm going to use context log info, and I'm going to have a simple logger tag. And I'm going to inject my message in this interpolated string, and I'm going to keep the behavior same. So the way that this behavior works is that upon the reception of this message, the actor can change its behavior, but in this case, I'm going to keep the behavior to be the same. So I'm going to spin up a logger. So I'm going to have my context spawn. I'm going to create a small child actor. And I'm going to use ctx spawn, and I'm going to use simple logger. And I'm going to give a name. So let's call this logger. And I'm going to create my hotel actor. So hotel as context spawn, and I'm going to use my hotel actor, which I need to import. So hotel, I'm going to give this ID, let's call this test hotel. And I'm going to use the name test hotel for the actor as well. So test hotel is the persistence ID of this actor, and this is the actor identifier if I want to access that within the actor system. Now these constructs, for those of you who haven't seen Akka before, they might seem a little strange, and that is because an actor is never actually spawned through a constructor of the class, but rather it's spawned through this construct context.spawn with the behavior described by whatever invocation I might pass as the argument, and the actor name obviously. All right, now I'm going to send a message to this hotel. So I'm going to have hotel tell. And the way that we send a message to an actor asynchronously is through a method called tell, which is denoted in Scala with this very interesting name, ! Which is an operator. So I'm going to use a make reservation that I will import from the model. And the make reservation obviously will have a bunch of parameters. So the guest ID, I'm going to have my name. And the start date, I'm going to use date from Java util, so not Java util, Java SQL, date value of, and I'm going to use 2022 July 14th, which is the day of recording, and I'm going to use another date, let's say July 21. So we're staying for a week at room 101, and the logger as the reply to actor, which this hotel actor will interact with. So once the hotel receives the make reservation message, it will perform all this logic. It will persist this event into Cassandra. Then it will reply to whatever actor I specify, which is the simple logger, that the reservation was created. And the behavior of the root actor system is going to be empty. So I'm going to create an actor system. So let's call this system as actor system with the root behavior. So root behavior. And the name, let's call this demo hotel, which will probably be a better name for this application. So hotel playground, I'm going to use hotel demo. And this actor system, let's say, will terminate after 5 seconds. So system scheduler, and I'm going to use schedule once. And for 5 seconds, I'm going to run a runnable, and I'm going to say system terminate. Now, 5.seconds doesn't exist without an extension method. Scala offers that. I'm going to import a package called Scala concurrent duration everything. I teach this in my Scala advanced course, how extension methods work. So notice the expression is very interestingly readable. And I'm going to import the execution context, which is a Scala native thread pool for running this little action. So I'm going to import system.execution context. And at this point, we should have a runnable application. We need to figure out if Cassandra is working, and by the look of it, it seems that Cassandra is working. We can connect in another terminal window. I'm going to use docker ps to find out the name of the Cassandra Docker container. I'm going to copy that, and I'm going to run this command, docker exec-it, and I'm going to paste this, and then I'm going to use CQL shell, CQLSH, to start the Cassandra query language shell prompt. And if this works, then that means the Docker container is up and running. We should be able to run this application. So this is going to be our first run. It will take a couple of seconds for the compiler to compile all our code that we wrote in the last half an hour. And notice that we have some logs here. And we have the demo hotel using the Java serializer. And notice that the logger got the reservation accepted. So the reservation accepted was logged by the logger, which means that the event was persisted. Now, due to application.conf, Akka persistence already knows which persistence store we're going to use. So in this case, we have here under Akka persistence journal, we have Akka persistence Cassandra journal, which is a smart journal that will automatically create the appropriate tables for all the messages and the events that we're going to store in Cassandra. So here in SQL shell, I can now run this command, select star from a table called akka.messages. So if we see something like this, if we see a row in akka.messages, this, what you see here, this binary string, is the binary encoding of the reservation accepted event that was persisted in Cassandra. This table was automatically created by Akka persistence, and you can check the tag here called test hotel. So this is called the persistence ID. The persistence ID is the unique actor that wrote this event into the database. So the persistence ID is called test hotel, which is the exact identifier that we added at the application. So the make reservation effect works correctly. We can now implement the rest of the effects. Now, looking at the hotel, if we go back to the logs of the running of the previous application, notice that we also have state changed here. So state changed means that our handler, our event handler, worked correctly in the sense that after the event was persisted in Cassandra, the internal state of the actor was changed to the set that now contains the reservation with the name Daniel. The hotel is test hotel. The dates are as I typed. The room is 101, and the randomly generated string, which is the confirmation number. Now, the best thing about this is that if I restart the application and I don't send any more messages to the hotel actor, so in hotel demo, I cut out the make reservation message or command, the hotel, because it has the test hotel persistent actor, it will ask Cassandra for all the events that were associated to that persistence ID. And therefore, the state will still change to the reservation that I added in the previous run. So the hotel, upon starting the application, will restore the entire state as if nothing had happened. So I'm going to cut the make reservation thing, and I'm going to run the hotel demo again. So this time, no further events will be persisted to Cassandra, but notice that we also have state changed from the hotel because the hotel replayed all the events that are already in Cassandra associated to that persistence ID. So if your application crashes, or if you need to upgrade it or restart it for any reason, all your actors will restore their current state. So back to the hotel actor, we now need to handle the change reservation and cancel reservation commands. Now, in this case, we need to find the old reservation by the confirmation number, and if we don't find any reservations, we need to reply with a failure. If we do, then we need to create a tentative reservation and still find a potential conflict with the set of reservations that we currently have. If there is such a conflict, then we will return a failure. Otherwise, we will persist a reservation changed event, much like we did earlier. All right, now let me find the old reservation. So I'm going to have my old reservation, and I'm going to use an option here. I'm going to say state reservations find, and I'm going to find by confirmation number. So understand underscore confirmation number must be equal to the confirmation number that I want to change. Then I will need to create a new reservation. So I'm going to have my tentative new reservation, so new reservation option as old reservation option, and I'm going to map. And given the reservation that this option will store inside, I'm going to say res copy, and I'm going to copy just the start dates, end dates, and room number because everything else is the same. So start date equals start date, and end date, and the room number. All right, so if there is such an old reservation option, the new reservation option will also contain a value. Now, we are going to have a tentative reservation updated event. So I'm going to have, let's call this reservation updated event as, I'm going to suffix that with an option as well. And I'm going to have my old reservation option, and I'm going to zip that with a new reservation option. And this will be an option containing a tuple. And because we have a reservation updated event, I need to store the old reservation and the new reservation in this data structure. So I'm going to then map that, and I'm going to say reservation updated, I think, and the constructor is called tupled. So this is going to be an option of reservation updated. This is the event that I want to persist to Cassandra if these two options exist. Now, I need to find the conflicting reservation if there is such a thing. So I'm going to have, let's call this conflicting reservation option as new reservation option, which was computed before. And I'm going to run a function called flatMap. And considering the tentative reservation inside, so tentative reservation, then I'm going to run the same logic as before. So I'm going to have state reservations find, and I'm going to say the reservation contained in the state does not have the same confirmation number, because otherwise, obviously, it will conflict. So our confirmation number must not be equal to confirmation number. And the intersection. So I'm going to have R intersect with this tentative reservation. So we have a bunch of options here. We need to treat them. So I'm going to run a tuple. So I'm going to have reservation updated event option and the conflicting reservation option. And I'm going to pattern match against these two. Now, in case we get a none and whatever, it means that there is no reservation updated event option because the old reservation could not be found. This whole option depends on me finding the old reservation number by confirmation. So I'm going to return some sort of confirmation failure. So I'm going to have effect.reply, and I'm going to reply to the reply to actor that this change reservation command contains. And I'm going to return a command failure. I'm going to say cannot update reservation, and I'm going to use confirmation number, and I'm going to use not found. Now, in case we get something and some value here in conflicting reservation option, again, this is going to be a command failure because there's already a conflicting reservation for what I will want to do. So I'm going to return another command failure. I'm going to say cannot update reservation confirmation number, conflicting reservations. Cool. And in case we get a sum with the res updated, this is the event, and none, that means the happy path. So this is the happy path, in which case I found the old reservation option and I did not find the conflicting reservation, then it means I'm going to persist my event. So I'm going to have effect.persist, and I'm going to persist this res updated thing. So res updated because I've computed that beforehand. And I'm going to say then reply with the reply to actor, and I'm going to return s arrow, and I'm going to use this res updated event as before. And now I can safely remove the effect none thing because I've already implemented my to do. So I'm going to keep the logic here by the change reservation case. All right. So we have our effect. Now let's try this out. I'm going to go back to the hotel demo. We already have a reservation in the database. I will want to try to change a reservation. So I'm going to say, let's call this change reservation with the confirmation number, start date, end date, room number, and reply to. I'll need to fetch the confirmation number from the logs, which is this thing, because it was randomly generated before. So I'm going to copy that, and the change reservation will have the confirmation number, and I will want to change my reservation. Let's say I want to prolong my stay for another 7 days. So I'm going to change my reservation to 2022-07-28, and I'm going to maintain the same room number. Okay, let's try this out, and let's see if it works. All right, so we have our logger. So we have a reservation updated with a old reservation and the new reservation, which will be found in Cassandra. So if we navigate back to Cassandra and we select star from Akka messages, notice that we now have two events stored in Cassandra. This is the reservation created, and this was the reservation updated. This is great. Now, Let's go back to the hotel, and let me also treat the case for the reservation updated event in my event handler because I didn't add that. So I'm going to have a case for reservation updated from the old reservation to the new reservation. Again, I'm going to print line state changed, and I'm going to create my new state. So I'm going to have new state as state copy, and reservations is going to be state reservations minus the old reservation plus the new reservation. Because I implemented the equals and hash code methods on reservation beforehand, adding and removing items from a set is very easy. And I'm going to return the new state as well. Good. Let me go back to the application. Let me comment out the message that I sent because these events are already in Cassandra, and I should now see 2 state changes in my hotel actor. Right, so we have state changed. So the first one is the reservation between 14th of July and 21st. Then we have a state changed from the 14th to the 28th. And this is great because it maintains the same confirmation number. Notice that the actor replays all the events to restore its old state. Now the canceled logic is very similar, so I'm going to speed things up a bit. I'm going to simply find the old confirmation by number in my state. If I can find it, I'm going to persist the event, the cancellation event, and I'm going to reply with the right response. Otherwise, I'm going to return a failure. And in my event handler, I'm going to treat the cancellation event, and I'm going to update my state. Now let's test it out. So here under the hotel demo application, I'm going to also send a cancel reservation for the same reservation confirmation number. We don't really need to send the make reservation and change reservation messages again because the hotel actor will recreate the state. So I'm going to say hotel, I'm going to say instead of change reservation, I'm going to say cancel reservation. So cancel reservation, and I'm only going to pass the reservation confirmation number and the logger actor, which the actor will use to reply back. So in this case, we will have another event persisted to Cassandra. So these events will be additive, but the state of the actor will be reconstructed after them. So let me run the application again. And we should see 3 state changes, 2 of them for recovery from Cassandra, and notice that the third one is a state with a set of empty reservations, which means that our reservation was canceled. And if we navigate back to Cassandra, we should see 3 events instead of 2. So notice that we now have 3 entries in the database. 1 for making reservation, 1 for amending the reservation, and 1 for canceling it. Of course, if I comment this code as well, and if I rerun the application, the state of the actor will be restored to an empty state. So a state with no reservations after replaying all the reservation events in the database. So our hotel actor should work correctly as of this moment. Now, for the real application, we're going to spin up many of these hotel actors, and we're going to randomly set the make reservation, change reservation, and cancel reservation commands to them as simulated by some external API. So here under actor, I'm going to create a new Scala class. I'm going to call this reservation agent or something like that. And this agent will be an object that will generate an influx of these events from some sort of external API. So this will simulate a large influx of commands to hotel actors. And I'm going to leave it as a to-do for now, because for now I'm going to focus on a single hotel, and then we're going to enhance the scale of this application. So back to the hotel. Now, the hotel currently implements the write side of the application. The read side has not been implemented yet. So from the command query responsibility segregation, we've only implemented the command part, which is implemented through event sourcing. We are also going to implement the read side of this application by creating another application here. So here under apps, I'm going to create a new Scala class. I'm going to call this persistence query demo, and I'm going to make it an object because this is going to be a standalone application that will simulate one of those hotel apps that will monitor all the events associated to a particular hotel. Now that I think about it, instead of persistence query demo, I'm going to call this hotel event reader or something like that to denote the R part from CQRS. So this is going to be a standalone application which will monitor all the events associated to a particular hotel, obviously independently from the right side of the application. So in order to implement the read part from CQRS, we're going to use an Akka persistence feature called Akka persistence query. This is why I originally named this persistence query demo, but it's actually better named by its purpose. So I'm going to use Akka persistence query to monitor all the events associated to a particular persistence ID, which is how a hotel is uniquely identified. So I'm going to create an actor system. So I'm going to say system as actor system that I'm going to import, and I'm going to use behaviors empty. I don't really need this actor system to contain any sort of actors, so I'm going to leave it at that, and I'm going to call this hotel event reader system. Cool. Now, this system will create what is called a read journal. A read journal is one of those little utilities that will monitor all the events in the persistence store, in this case Cassandra, obviously, associated to a particular persistence ID. So I'm going to create a read journal and I'm going to use persistence query, and I'm going to import that from the system. So the persistence query is indeed based on actors, and I'm going to say read journal for. I'm going to add a type argument, and this is called Cassandra read journal. And I'm going to import that. Make sure you import from the Scala DSL, because we're writing Scala, of course. And the argument of that is going to be Cassandra read journal dot identifier. So every journal will have a unique identifier by which persistence query will identify it, because in a real application, we can have persistence query with a variety of stores. So I'm going to use this Cassandra read journal. Now, with this read journal, we can fetch all the persistence IDs and all the events by that persistence ID, which is how a hotel is identified, or by tags. Let me show them in turn. So all persistence IDs. If you want to monitor a specific one, I'm going to say persistence IDs as read journal dot persistence IDs. Now, because persistence IDs can come and go because you add new actors in your database, this persistence IDs updates over time, which is why this is called a source of string and not used. I'm going to explain what the source is. Come from Akka Stream Scala DSL. This is an Akka Streams thing. And Akka Streams is a powerful library that will allow you to deal with an infinite amount of data from a variety of sources, which is why this persistence ID is an Akka Streams source. Now, in order to consume the source, you need to connect it to some sort of sink. So I'm going to say consumption sink as sink from Akka Stream Scala DSL, sink for each print line. So these are, for now, static components, and if you want to trigger an active stream, you will have to connect them. So I'm going to say connected. Let's call this graph, because if you connect a source with a sink, you'll get a graph. I'm going to say persistence IDs dot to consumption sink. And if you want to trigger the connected graph, because right now it's static, and materialize all the appropriate resources, sockets, and so on and so forth, you would say connected graph dot run. Now, this run method requires an implicit so-called materializer, which has the appropriate resources to allocate for the stream components, which is why I'm going to mark this system, this actor system, as implicit. This also contains an actor materializer. This is an actor system of whatever. Cool. Now, I'm going to type in a main method, and I'm going to call this connected graph.run in this application's main method. Now, if you call connectedGraph.run, you will print all persistence IDs as they come in my hotel application. So if I spawn another hotel with another persistence ID, it will pop up in this little application. For now, we only have a single persistence ID, which is that of the only hotel that we have, which is called test hotel. Now, in this case, let me go back to the application. We will see a single row being printed to the console. So right now, this spins up the appropriate resources, and notice that we have test hotel being printed. Notice that the application is currently running. So if by any chance there's another actor with a different persistence ID to persist an event to Cassandra, then you will see that persistence ID pop up in this little application as well. Now, this read journal is very powerful because not only can it fetch all the persistence IDs, but it can also fetch all events for a persistence ID. So for instance, if I want all the events associated to my test hotel, let's call this events for test hotel as read journal dot, and I'm going to have events by persistence ID, and I'm going to pass my persistence ID test hotel. Now this function takes a bunch of arguments to identify a sequence number for all the events by persistence ID because your events might be quite a lot in your real-life application. I'm going to simply fetch all of them from 0 to long.maxValue so that we can fetch all the possible events for this test hotel. Of course, this is also a source, and the source wraps an event envelope, which we'll have to unwrap to obtain the actual event that was persisted. So I'm going to run a map on that. So I'm going to say .map, and I'm going to extract the event out of that event envelope. So I'm going to parse that out. Then I'm going to map again, and I'm going to use a partial function that will run a pattern match automatically. So in case we get a reservation accepted for some sort of reservation, let's say I'm going to print something out. So I'm going to say print line, I'm going to say making reservation, and I'm going to inject res inside. And I'm going to do the same for all the possible cases. So I'm going to duplicate that. So in case we get a reservation changed, I'm going to import the whole model here. And I'm going to say reservation updated for the old reservation to new reservation. I'm going to say changing reservation from, and I'm going to use old reservation to new reservation. And in case we get a reservation canceled, I'm going to say canceling or removing reservation, and I'm going to inject res inside. Now, because I'm turning every event into the outcome of print line, which is unit, I don't really care about absolutely printing anything. So I'm going to say in main, I'm going to have events for test hotel. I'm going to say run with, and I'm going to plug in a sync.ignore. So I'm going to say sync.ignore. And instead of run with, I'm actually going to say to sync.ignore.run so that we have a similar approach to the previous example. So in this case, the read journal will fetch all the events associated to the test hotel. So it'll interrogate Cassandra for all the messages associated to test hotel, and it will print the appropriate string depending on that particular event. We can simply run this independently of any other application. All right, so we have making reservation, changing reservation, and canceling reservation in this order because that's how these events were persisted. Now, this part is where things might get a little confusing. The hotel event reader, this application that we have right now, is the Q part from CQRS, not the R part, the Q part from CQRS. So it's an independent reader. Now, this standalone application might also quote-unquote write data to the database, but for its own internal or separate purposes. For instance, this particular application might be specific to this hotel. So we might want to block the calendar days for which a room is booked, or store the reservations by guest for easier queries, and so on. So notice that everything that we might want to write into Cassandra is for its own internal purposes. We might as well write to a whole new different persistent store, but why use a different persistent store when we have Cassandra already? So whatever this application may end up writing to Cassandra, it's for its own internal read model. All right. So instead of simply printing making reservation, changing reservation, and canceling reservation, I'm actually going to store some data to Cassandra that is specific to this hotel for easier queries later. So now's the time for me to actually add all those tables that I added at the beginning of the video with a table setup.cql. This contains all the table definitions for the Akka and Akka snapshot key spaces in Cassandra, which Akka persistence automatically creates, but we're going to have to create these manually when we connect to Astra DB. And we are going to also have some hotel and reservation related tables. So I'm going to copy all of this from create key space hotel all the way to the end. And notice that in this case, we also have a materialized view. So depending on the Cassandra version that you have, and if you've enabled materialized views, the experimental feature in Cassandra, this may or may not work. In this particular video, I'm not going to use materialized views. So this command will fail, but I'm fine with that. Materialized views are an excellent way of keeping some tables in sync. So I'm going to copy those. And in my SQL shell, I'm going to paste everything. So run all the commands, and notice that the materialized view doesn't work because we have materialized views disabled, enabled in Cassandra YML. So you can enable that in Docker container if you wish. I'm not going to use that for this video. All right, so we're going to ignore the materialized view. You can enable that if you want. So right now we have all the tables for reservations, hotels, and so on and so forth. Let's go through them in turn real quick. So in the key space hotel, we have a type called hotel address if you want to fill some data over there. We have hotel.hotels, and every hotel will have an ID, a name, phone, and an address. So this is very useful if you want to actually fake your data with some actual addresses and so on and so forth. There are some Python packages that do that job very, very well. We're not going to use these tables for this video, but rather I'm interested in available rooms by hotel date. This is very important. This is essentially a table with calendar days that we can block if a reservation is made. So for every hotel, for every date, for every room number, we have a flag whether that room number in that hotel is available at that date. So we can fill all the calendar days, say for a year, for a particular hotel and make the rooms free. And whenever we have a reservation, we're going to block all these calendar days. As for reservations, we have this key space specific to reservations. We have the reservation.address, also a custom data type. We have reservation.reservations by hotel date. So for every hotel, for every start date, and for every room number, we have a confirmation number for a guest ID and the end date of their trip. So we're going to store these reservations with this primary key, the tuple hotel ID, start date, and room number. The materialized views you're going to ignore, and reservation.reservation by guest is another table that is very useful for querying. So for every guest last name and confirmation number, we can find a particular reservation with a hotel ID, start date, end date, and so on and so forth in some sort of centralized fashion. Also, if you want to store data about the reservation guests and amenities by room, if you want to add special features or other kinds of commands, for example, if you want to add extras to bookings, for example, a special room or a breakfast in bed or what have you, you can add them in these tables. I'm not going to use them for this video in the interest of time. So the critical tables are reservations by guest, reservations by hotel date, and the available rooms by hotel date, so the calendar days. Right, so in this hotel event reader, we can actually write to these tables. Now, when we make a reservation, we need to block the calendar days associated to that reservation, which means that the room must be free, which means that the calendar days need to be in the reservations table, which means I'm going to create another application that will populate these tables for a particular calendar duration, let's say a year. So I'm going to create a new Scala application, and I'm going to call this Cassandra Table Cleaner, and I'm going to run this application whenever I need a fresh state of Cassandra. Now, in the interest of time, I'm going to speed things up a bit. So for every hotel, right now we have one. For every room, which is, in my assumption, 100 rooms per hotel, and for every day, and I'm assuming a year worth of data, I'm going to clear up a day in the calendar for that particular hotel for that particular room. Now I'm going to slow things down a bit because I'm going to show you how we can write an item to Cassandra. I'm going to create an actor system, so system as actor system from Akka actor typed with behaviors.empty, and I'm going to call this Cassandra system. And I'm going to create a session, which is a Cassandra session that will allow me to execute queries. So I'm going to use Cassandra session registry. And I'm going to use Cassandra session registry from the Scala DSL package because otherwise we're going to have some type conflicts for that system. And I'm going to say session 4. And the configuration path you can find in application.conf. It's called Akka projection Cassandra session config. So this is the string that we want. So I'm going to go back and write that string. So Akka projection Cassandra session config. And with that session, I can actually execute a query to Cassandra. So I can say session.execute write, and I'm going to pass my insert. Now I have to be really careful about this insert because the names of the columns need to be matched exactly. So because I don't remember them by heart, I'm using the appropriate file. Now, because this is an Akka stream source, I'm going to pair it with a sync and return a future that will simply run all these statements. After that, I'm going to run a future that will truncate all the existing tables from Cassandra. Now, this contains all the Akka tables, the Akka snapshot, and also the reservation tables that I want to clear. Now, all these statements will run as futures as well, and I'm going to print something in case something goes wrong. Now, once I've created the clear rooms and this future sequence, I'm going to add the clear rooms to this list. And after the future finishes, I'm going to run an onComplete. And in case this thing finishes, I'm going to print line a little statement. So I'm going to have a print line with all tables clear or something like that, and then I'm going to say system.terminate to finish the application. So this is a quick application that will simply clear all the tables and insert true in all the calendar days for an entire year for this test hotel. Now we can run this application by adding a main method at the very end of the file. So I'm going to type in a main, and I'm going to call this clear tables, and we can run this application, which will probably take a few minutes for our Docker container to execute so many queries. So we have roughly 40,000 queries that will be executed by Cassandra, so I'm going to speed things up a bit. All right, cool. So our application finished, and we can test the result of this application by inspecting the hotel available rooms by hotel date, because this is the only table that actually has some data. So I'm going to copy this table name. I'm going to navigate back to my SQL shell, and I'm going to say select star from this little table, and let's say limit 10 to not fill the entire screen. And we have for the test hotel for the date, the 1st of January 2023, for the room number 1 to 10, and is available true. So we have for every number, for every date, we have true. So before every test, we're going to run this application to clear our Cassandra tables. So now that our Cassandra tables are clear, let's go back to our hotel event reader, which is the persistence query based read application. And instead of making reservation, changing reservation, and canceling reservation just as prints, we're going to store some data into Cassandra just for this application to read. So let me go ahead and create a simple method called make reservation. And I'm going to have a reservation as an argument. And this will simply execute some statements in Cassandra to block all the calendar dates and insert some values in the reservation tables. Now I'm going to create some variables that will deconstruct the reservation, and it will tell me which days I need to block in the calendar. Now, in order to execute the statements in Cassandra, I will need one of those sessions that I built for the other application. So getting to the Cassandra table cleaner, I'm going to copy the session and I'm going to paste it in my reader application. So this is the Cassandra session. And I'm going to have my val session as Cassandra session registry, whatever, and I'm going to use this session to execute some statements. So for every day in this days blocked, I'm going to execute a statement. I'm going to return a list of futures. So this is going to be some, let's call this blocked days futures as a for comprehension, and for every day in 0 until days blocked, because that is an int, I'm going to yield a future obtained by session dot execute write, and I'm going to write the statement to update, and I'm going to update the hotel's available rooms by hotel date. So I'm going to copy this name, paste it here. So I'm going to say update this thing set, and I'm going to say is available to false, and I'm going to have a where clause, and in the where clause I'm going to have my hotel ID is the hotel ID, so hotel ID. And I'm going to make sure I'm wrapping this in single quotes, and date is equal to single quotes, and I'm going to expand a variable here, which is start local date plus days, and I'm going to have days, and room number equals room number. And I'm going to make sure I have the right amount of single quotes. Now, after I block the days in the calendar, I also need to add some rows into the reservation by hotel date and reservations by guest tables in 2 separate futures with 2 separate statements. Now, just to be able to investigate whether any of these statements failed for any reason, I'm also going to add some recover callbacks so that we can inspect what went wrong in that case. Now, in order to be able to run these recover callbacks, we will need some kind of execution context, which will be provided by the actor system. So I'm going to have to import system.execution context so that we can run all these callbacks. So now we have a sequence of futures, which I'm going to run with future.sequence. And I'm going to import Scala concurrent future, and I'm going to have my reservation guest future and reservation guest date future and all the blocked days futures. So blocked days futures dot toList. And then I'm going to map this entire future to return some sort of unit. So this is going to be a future unit, and this will simply finish when all these statements complete. Now at this point, the make reservation call is complete, so we are executing these statements in Cassandra and it returns a future unit. So we can actually invoke this future when we found a reservation event. So we can say make reservation with res. Now in this case, we will need to run a map async instead of map because make reservation is not a plain value, but it's a future. So I'm going to change that to map async with, let's say, a number of threads, like 8 threads, and we will run the same function that will return some futures. And for the cases where I simply return some print lines, I'm going to return future.successful with unit so that we only return a future wrapping a plain value. So this is a placeholder. I'm going to add a to-do here to insert the appropriate data into Cassandra if we are changing reservation and canceling reservation in that case. So notice that we only have reservation accepted if we are making a reservation. At this point, we can start the application and listen for all the events that are associated to this persistence ID. And after that, we can spin up our little hotel actor and try to persist some sort of event. So I'm going to run this hotel event reader, and we have a running application. Let's see if nothing goes wrong. So all good so far. And I'm going to start my little hotel demonstration. And in my hotel demonstration for test hotel, I'm going to simply create a new reservation. Remember, at this point, our Cassandra database is free because we executed the Cassandra table cleaner. So all our tables are fresh. So at this point, we can run our hotel demo as well, which will start persisting those events in Cassandra. And this hotel demo will have a state change. So the reservation was accepted. And in Hotel Event Reader, notice that we now have a log for making reservation, for reservation Daniel, test hotel, and so on and so forth with this confirmation number. Unfortunately, it seems that at this point we have some syntax error in our statements, but these are surfaced out by our recover callbacks, which is a good reason why we added them. So let's go back and let's inspect our syntax. So we have room day blocking failed. We have a syntax error, no viable alternative at where hotel, because we don't have a space. That is okay. Then we have a syntax error for reservation for date failed, which is my second query. And we have no viable alternative at input closed paren. And we have insert into reservation, we have values, and then again, no space because we have some open and closed parentheses, but the values here doesn't have any space, and likewise for the third element. Now, let me close my hotel event reader. My hotel demo has already finished. So the hotel event reader can simply restart at this point because the event has already been persisted into Cassandra, so this can simply pick it up again. So let me start my application, and hopefully my syntax is right for the Cassandra. So notice that we have fewer errors here. So the room day blocking was successful, but the reservation for date failed. Again, a syntax error. We have a no viable alternative at the closed paren. Now in this case, I think it's something different because the guest ID is Daniel, and the guest ID is supposed to be, if I remember correctly, a unique identifier. So the table setup says that the guest ID needs to be a unique identifier, so UUID, and the UUID obviously doesn't conform to the string Daniel. So here under the hotel demo, I'm going to create a make reservation, not with Daniel, but a unique identifier. So I'm going to have a UUID dot random UUID dot to string. Now at this point, I should invalidate the Cassandra messages, so all the events that were persisted to Cassandra, which is just one, and let me make the reservation again. So here under the CQL, I'm going to say truncate akka.messages so that we don't run that table cleaner again, which takes a little while. So I'm going to close the hotel event reader and then spin up the hotel demo again and the hotel event reader in any order. So I'm going to spin up the reader again, and then the hotel demo again, and let's see what happens. All right, so we now have a single reservation because we only have one event, and the hotel event reader, notice that we have making reservation and no other syntax error. And this is great because right now we have some reservations being stored into the Cassandra table specifically for this particular hotel. So we should be able to find an entry here under reservations by guest and an entry under reservations by hotel date. Let me try reservation and reservation by guest. So I'm going to say select star from this table where, and if I go back to my table setup.cql reservations by guest has the primary key guest last name, which is RocktheJVM, and confirmation number. Now, I'm going to say where guest last name is, quote, RocktheJVM, and the confirmation number, so confirm underscore number is, and I'm going to fetch that from the logs, which is this little code at the bottom. So I'm going to paste that here in between quotes. Let's see. And we have an entry. So the guest last name is RocktheJVM. Obviously, you can enhance this data with some real names for your guests. The confirmation number, end date is the 21st of July, and the start date is the 14th of July, as was requested by that event. This is great. We can try the same for the other table, but I'm pretty sure we're also going to have the data there. So at this point, we have a first step towards full functionality of the read side of this CQRS application. We can also add another method here to remove a reservation and also to change a reservation. Now, the implementation of the removal of a reservation is comparatively simple because we can simply start from the previous implementation and just unblock the days in the calendar by setting their flags to true. And instead of inserting into the reservation tables, we're simply deleting where the conditions hold true for the hotel ID, start date, and room number. So in the case for cancellation, we can simply call this remove reservation. So instead of this to do, I'm going to say remove reservation for this reservation. And in my hotel demonstration, I'm going to run a cancellation, and we're going to see if that reservation is still in my tables. So here under the hotel event reader, I'm going to run this application again. So this will simply look for all the events. So making reservation, which is okay because the event is in the database. And in my hotel demo, I'm going to issue the cancel reservation command, which will persist the event, which will then be listened to in the hotel event application. So notice that we have a state change. And now we have command failure cannot cancel the reservation, this one, because it's not found. And this is completely normal because the reservation confirmation number is changed this time. So I need to change the confirmation number and I need to paste it here and rerun my application. Let's see. So it's good that we have all these fail-safes in the code. All right, so the state was changed to an empty state, which is good. And notice that we now have canceling reservation for this particular confirmation number. But the reservation removal for guest and for date failed. Again, a syntax error. Let's go back to the hotel event reader and understand what went wrong. So the one for the guest failed, which is the second one, because we have a mismatched input and expecting empty paren. I'm going to remove this parenthesis. It's probably a token from the last one. And the other one says undefined column name room number because I'm used to this camel case instead of the Python case. Let's try running the application again, and we should see a cancellation. All right, so notice that we have canceling reservation, which is great. We have the cancellation effect being performed. And if I try running the select statement again, I should not see any more entries in my table. So if I run the same query again, notice that nothing shows up. And this was great. A reservation was simply removed from my hotel. My room is free. Now, in the case of a change, we only need to remove the existing reservation and add a new one. Now, we need to run two futures, which is going to be combined in a for comprehension. So in remove reservation for the old reservation, and I'm going to add a new reservation. So make reservation for the new one. So new reservation, I'm going to yield unit. And because removal and making worked correctly because we've tested them a couple of minutes ago, we don't really need to test the reservation updated because we're pretty sure it will work fine. So we've fully implemented the CQRS pattern for the entire application for a single hotel. It's time we scaled this up a bit. So I'm going to create my little reservation agent, and I'm going to define some messages that this agent will receive. So here I'm going to create a simple trait that I'm going to call hotel protocol. And this hotel protocol will be the protocol that the reservation agent will handle. So this actor ref here instead of any will be an actor ref of hotel protocol. And this will extend command, of course, as before. And I'm going to have a case class. Let's call this manage hotel. In case this reservation agent will manage a new hotel. So manage hotel, which is a hotel with an actor ref of type command. And this extends hotel protocol. And another one, I'm going to call this generate, which will generate a number of events or commands, rather. So n commands as an int for the hotels that this thing manages. So this extends hotel protocol as well. Now, considering that the command failure and all the events are going to be sent back to the reservation agent, I'm going to mix in the hotel protocol in all of them. So I'm going to mix in hotel protocol in this domain model for all of these messages. Now, in real life, this reservation agent would have to report to some sort of user-facing API or an HTTP service or a user interface or something like that that will receive all these commands, and this reservation agent will pass all these commands all to the hotels under its jurisdiction. But in this case, I'm going to have the reservation agent generate all these sorts of events so that we can scale our application and see it perform live. Now, this reservation agent is only auxiliary to our application. It's not really relevant to the CQRS pattern that we've already demonstrated, so I'm going to speed it up a little bit. So enough music, we wrote a lot of code and we haven't tested it. This reservation agent would simply generate delete or cancellations with probability 5%, changes, that is updates with 15%. So I've added these two together with a 20% total and 80% with make reservations. So this is the proportion that I'm going to go for in this application. Obviously, you can change the numbers as you see fit. Now, we're going to scale things up a bit by creating this reservation agent and making it manage more than one hotel. Now, in order to be able to test it, we are going to modify the Cassandra table cleaner to manage not just one hotel with the name test hotel, but let's say 100 hotels with the name hotel_I or something. So instead of a simple list, I'm going to say 1 to 100, and I'm going to say map for every I. I'm going to return the name hotel_$I. And this will mean that we will have 100 times 365 queries to Cassandra, so 3.6 million queries to Cassandra. So as you can imagine, it's probably going to take a while, so feel free to run this application while we are modifying the rest of our code. All right, so with my application collapsed, I'm going to create another application to automatically generate a large number of events. So I'm going to call this reservation generator, and I'm going to make it an object with a main method. So in this case, all I'm going to do is spin up a reservation agent and a bunch of hotels. So I'm going to spin up 100 hotels, and I'm going to tell the reservation agent to manage every single one of those hotels. After that, I'm going to generate messages or commands in bursts. So 100 times, I'm going to generate 10 messages at a time. So 1,000 total messages at 100 different hotels. So at this point, we can simulate an entire application that manages 100 hotels at the same time with messages coming from whatever front-facing API we might want to imagine. Now, from the persistence query side, so from the hotel event reader, we can monitor all the events associated to a particular hotel. So in events by persistence ID, we can ask for hotel_37 or something, and monitor all the events associated to this particular hotel. So at this point, we can spin up both of these applications, this one and the hotel generation app. So let me go ahead and do that. I'm going to start hotel event reader for hotel 37. So at this point, we shouldn't have any kind of messages. But once I start the reservation generator, we should start seeing some events associated to this particular hotel. Not too many, but some. All right, so notice that we have a bunch of messages being generated in spurts, and we have some making reservation, changing reservation, and so on and so forth as they come for hotel number 37. So this application can monitor all the events associated to a single hotel. Obviously, you can spin up multiple instances of this hotel event reader for multiple hotels if you'd like. All right, so at this point, our CQRS application is complete at scale. Now, the final piece, the crown jewel of this application, is to run it on a cloud-managed Cassandra service, which is Astra DB from DataStax. This is essentially Cassandra as a service without you having to do pretty much anything for it. So we will take this application and we will deploy the data model on a cloud-managed service. So we will navigate to astra.datastax.com and just sign in with your username and password, or sign up if you don't have an account. Creating one is very easy. It's completely free. So in a couple of minutes, you should be ready to start. So you can pause the video and do that if you haven't done so already. And after you log in, you'll have this dashboard in front of you, which will show you all the Cassandra databases that you have under your account. I already have one because I created one in preparation for this video, but for this particular recording, I'm going to create a fresh one. So I'm going to click this button to create a serverless database, and I'm going to follow this little wizard. The database name is going to be, let's say, RocktheJVM CQRS demo. And a key space name, I'm going to start with RocktheJVM, but we are going to add all the key spaces, including Akka, reservation, and hotel for our database. We're going to select a cloud provider. I'm in Europe, so I'm going to click Europe, and I'm going to select one of these regions, and then I'm going to click this blue button to create the database. This should only take a couple of seconds. And after the spinner finishes, you'll get to the client ID, client secret, and token, which were already created automatically by the Cassandra service, but we will create a new admin token from scratch with heightened privileges, so you can click this blue button to go to the database. After the spinner finishes, you'll get to another dashboard, which is particular for this CQRS demonstration database that we've just created. Now, for this database, I'm going to create a new token as I promised. So click on your current organization, click on organization settings, and go to token management, and you will select an administrator user, which is the topmost privilege for everything that you may want to use this database for. So you'll click this button to generate the token, and then you'll copy the strings in this dialog box. Now, here's where you need to put them. I'm going to copy the client ID, and I'm going to navigate back to my application. I'm going to go to application.conf, and here I have a section that I've commented out, which is under the DataStax Java driver. We have a section for basic cloud and advanced auth provider. I want you to uncomment that section. The secure content bundle is going to be an empty string for now. I'm going to show you what that bundle is. And here under username, I'm going to paste that client ID, and the password is going to be the client secret in this dialog box. Now, I'm not really afraid of having them in the clear in this video because I'm going to remove the database anyway after this recording, so there's no worries about that. Cool. So you'll have your username and password already here in the configuration. I've already set this for you so that you don't need to care about that. Now, with these things in place, I'm going to create all the schemas and all the tables that we're going to need to interact with this Astra DB. So I'm going to navigate back to my profile, and I'm going to navigate back to my database. So let me navigate to the RocktheJVM CQRS demo, and I'm going to click this CQL console here in the middle of the screen so that I have access to a terminal, much like my Docker container. All right, so with this CQL.sh, I'm going to go back to my table setup.cql, and I'm going to create all the tables. Now, before that, I forgot, I need to add all the key spaces. So back to overview, I'm going to add a key space. I'm going to have a key space for Akka. And unfortunately, the UI has a little bug because after you create the key space, this little button is blocked, so you need to refresh the page. And I'm going to have to add all the key spaces, including hotels and reservations. So you can pause the video until you have 4 major key spaces. We have Akka, Akka snapshot, we have hotel, and reservation. At this point, we can copy all our table definitions. So I'm going to be very careful about this. We have Akka snapshot, and then I'm going to copy this one, go back to the CQL console, and I'm going to paste everything in this terminal. Let's see. So this works. Okay. Then all the tables in the Akka key space, there are the most of them. I'm going to copy that, paste them in the terminal. All right. Then after the hotel, we have everything inside. So everything in that section. After that, we have reservations. and everything with including amenities by room, although we aren't really using them for this application. And materialized views, as with the Docker container, the materialized views aren't really supported here, so we will ignore that for the application. Now, after we've created all the tables, now it's time to run our first demo application. Thankfully, we have one with a hotel demo. So I'm going to make a reservation first, and then I'm going to change it and cancel it once I have the confirmation identifier, the confirmation number. Now, before I run this application, we will need to go to application.conf and fill in this missing piece, which is the Secure Connect bundle. This is a zip file which will contain some connection certificates that will let you connect to Astra DB in a secure fashion. So navigate back to your database and click this Connect tab, and click on Java here using a driver. So connect using a driver in this section with Java. And the Java obviously is for Scala applications as well, being run on the JVM. And after that, you will have to download this little bundle. So click on this download button with Secure Connect bundle. And this will download a zip file which I want you to copy and paste into your source main resources. So I'm going to take it, and hopefully I can drag it all the way to my application. So I'm going to edit that. So under CQRS Cassandra Live, under source main resources. Okay. And then I'm going to click on this refactor button. I don't know why it's called refactor. So notice that we have Secure Connect RocktheJVM CQRS Live Demo. So this is the zip file which will contain all the required certificates. And then I'm going to right click on it, and I'm going to copy path and reference from the content root. So source main resources, this RocktheJVM CQRS demo.zip. Now at this point, all the configuration should be complete, and I should be able to run this hotel demo with a simple make reservation event. So let me run this application, and let's see what happens if this application runs. All right, so after a certain while, notice that we have some events here in the logs, and the state was changed, which meant that the persistence of this command was successful. So we can navigate to the RocktheJVM CQRS demo at the CQL console, and I can investigate if we have a message in akka.messages. So I'm going to select star from akka.messages, and if we have an entry there, then that means the event was persisted. And notice that we do have a single event here, which means that our application connected successfully. Now, let me get the confirmation number, which is this little fellow over here, and then I'm going to try to change it and cancel it. So I'm going to change reservation and cancel it with this confirmation number, and I'm going to run the hotel demo again. And at this point, we should see 3 items in akka.messages. Let's run this out. And after a couple of seconds, we should have 2 state changes. So notice that we have state changed and state changed. Now, I think we should have seen a state with an empty set because the reservation was canceled, but I think it's because of the fact that we are shutting down the application after 5 seconds, which is a bit too short. I'm going to shut it down after 30 seconds because now we're connecting to a cloud-based Cassandra and the latency might be a little bigger. So let me run the application again. Actually, I'm going to keep the change and cancel reservation. Let's see what we have. And after we run this application, we should see 3 items in the akka.messages table. Let's see. All right, so at this point, we have a state with an empty set, so that was probably the cause. We didn't give the application enough time to actually persist the events. So let's navigate back to CQL, and let's select star from Akka messages again, and sure enough, we now have 3 items in the table. So we can now safely connect to Astra DB with a demo application. What about our scalable application with persistence query? So right now we have Cassandra Table Cleaner, which will also connect to this cloud-based Cassandra service because of application.conf. So you can feel free to run this Cassandra Table Cleaner, but it will probably take quite a bit of time to run 3.6 million queries on a cloud-based Cassandra. But I have the privilege of video editing, which gives me some magical powers. So I'm going to simply run this application, and I'm going to snap my fingers, and I'm going to have all tables clear. So All right, amazing. Time travel is awesome. Now, at this point, we can run both of our applications, the hotel event reader and the reservation generator, to figure out if we have some events for a particular hotel. I'm going to say that the hotel event reader wants to read from a different hotel, let's say 82 or something like that. Now let me also collapse my little panels over here because my text is big and my screen is small. And now we're ready to run this hotel event reader, which will be in a waiting state because there are no events for hotel 82 at this point. So notice that the application is waiting. And at the same time, I'm going to start the reservation generator, which will create a lot of events. So let's try this out. And the hotel event reader should start monitoring some events. So notice that we have making reservation and maybe canceling reservation and so on and so forth. So we have quite a bunch of events happening here on our cloud-based Cassandra. And just to test whether these reservations were made in Astra DB, I'm going to pick a random reservation, maybe this one. I'm going to take its confirmation number, and I'm going to go back to my SQL shell, and I'm going to select something from that table. So I'm going to select star from, and the table is reservation dot, and we have reservation by guest. And I'm going to select star where, and I'm going to have, if I remember correctly, from the table setup, the table for reservation by guest had the primary key guest last name and confirmation number. The confirmation number I already have. The guest last name is always RocktheJVM. So the guest last name is RocktheJVM in all caps, and confirm underscore number is this little fellow in between quotes, semicolons. Let's see what we have. All right, this is awesome. So we have an entry here for the confirmation number, whatever, for the room number 37 between the 19th of November 2023 and the 22nd of November 2023, which matches the details in this reservation. So from 19th, 11, and 2211 for room number 37. So our reservations stored correctly in our Astra DB cloud-based database. All right, folks, so this was one massive journey, start to finish, with a real-life CQRS application written in Scala with Akka persistence and DataStax's official Astra DB database. I hope you enjoyed it, in which case I recommend you take a look at RocktheJVM. I have literally hundreds of hours of in-depth lessons like this. So check me out on YouTube, Twitter, and LinkedIn at RocktheJVM, and until next time, I'm Daniel, signing off.
And as always, don't forget to click that subscribe button and ring that bell to get notifications for all of our future upcoming workshops.